Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let us jump into it. Okay. Where is Sarah today? I wonder. Yeah, no one knows. No one knows. It's a mystery. So let's talk about what we did last time. So we went through a bunch of examples to learn how to do derivatives. We also started a new topic. Where are we? Yes, implicit differentiation. This was when we had an implicitly defined function, and like so, where your x's and y's are kind of mixed up and jumbled together. However, we still wanted to be able to find the derivative in this case of some dependent variable. So just because our function was written in a certain form doesn't mean that we don't care about calculus anymore. So we looked at how to actually do that, and it turns out that the trick was the chain rule. Intuitively, what we do is you go through, you differentiate as usual. However, whenever you differentiate an independent variable, you multiply by its prime because of the chain rule. You think of the independent variable that should be dependent. You think of the dependent variable as some inside function, right? So if you have x and y and you know that x is your independent variable, your y is thought of as some function of x. Therefore, whenever you differentiate it, you have to multiply by a derivative of the inside. And so you get, by the chain rule application, you just multiply by the prime every time. So if you only have x's and y's, you want to find dy dx, then differentiate as usual. However, whenever you differentiate a y term, multiply by y prime. This will go based on who is the independent versus dependent variable, which you can tell from the notation as I showed you. Which you can tell from the notation as I showed you here. So if I ask you for dy dx, it means that x is the independent variable, which means when you differentiate any x term, you just differentiate the x term according to the formula. If you differentiate a y or any other variable, you have to multiply by the prime. So if I ask you for dy dx, whenever you differentiate a y term, multiply by y prime. If instead I ask you for dx dy, what that means is whenever you differentiate an x term, you multiply by x prime. And when you multiply by the y term, you don't do anything, right? So you don't really do anything extra for the independent variable. You do it for the dependent variable, the functions that depend on that. So we did a quick example of that and spoke about that. I probably should have mentioned that we could multiply this by x over x, because I feel like in like a test or something, like I wouldn't type the answer that way, and I wouldn't really a textbook wouldn't really type the answer that way as well because of this 1 over x in here. So you'd probably multiply by x over x to simplify. And that would end up looking like y prime equals 6x squared y squared minus 8x squared minus 2xy minus 1 over 2x squared minus 6x cubed y. Okay. Based on a question, we kind of expanded a little bit upon how I actually went through and took the derivative of each term here. And the idea is, again, apply the product rule when it's necessary. If I have a x times a y, it's really an x times some function. It's two functions multiplying each other. You would need the product rule. The only difference is, again, whenever you differentiate a y term, you multiply by y prime, right? So that's basically it. What we're going to do is we're going to do a few more examples on implicit differentiation. We're going to talk about if it's even necessary. Why is it necessary? Is it just something that's cool? Or is it something that's actually needed? And then we're going to go a little bit farther than that. So we're going to pull it back a little bit, go on to some slightly easier examples than the first one I solved for you guys, and just kind of build back up to make sure we fully understand what implicit differentiation is about and why it's needed, when it's needed, that sort of thing. So let's continue with more examples. find y prime equals dy dx. Okay. And here's our first example, very simple. Xy equals 1. It's going to start very basic, just to kind of show you how you would do something like this with implicit differentiation, and also kind of point out the fact that we could actually do this without it. So here you'll notice here if we, without implicit differentiation. We could actually do this in another way. One, I could have actually just solved for the y, right? I could actually just say, well, this means that my y is equal to 1 over x, right? And of course, this is allowed because my x is not 0. How do I know that my x is not 0?
You can't have 0 in the denominator.
Well, yeah, but I wasn't guaranteed that it was not 0. Like, not having a 0 in the denominator would kind of force me to say that I should not divide by x in the first place. Why is this legal? How do I know that x is not 0? I actually do know for sure that I'm not dividing by 0 here. Do you see how I know that x is not 0?
Since it's x, y equals 1, anything that's 0 would be 0.
Right. So I know x is not 0 because of this. X not equal to 0 because xy equals 1. If x were 0, xy would be equal to 0. So I know I'm not dividing by 0, so this is completely legit, above board. Nothing can go wrong here, right? Division by x here, completely sanctioned. Everything is fine. So that's the first thing I want you to notice. Second thing I want you to notice is that now I can actually just differentiate this pretty easily. And that's going to be the derivative. So you might be wondering, do we need implicit differentiation here? So I'm also going to do it by implicit differentiation. So we can compare. So if I have xy equals 1, then I would go through and I would differentiate this as I usually would. X times y, this is a product of functions, therefore I'm going to apply the product rule. It's going to be 1 times y, differentiate the first term, leave the second. Then it's going to be x times y prime. Derivative of 1 is 0. Now I need to find the y prime, which means I can bring the y over that side. And then my y prime would be equal to minus y over x. And that's the answer. Now, there are a couple of things weird about this answer when I did it by implicit differentiation. For one, you'll notice that there's a y in the answer, which is very weird compared to anything we've seen before. Secondly, you might have the idea that, well, that's not the answer, is it? I mean, are these the same? Well, are they? Are they the same? Is implicit differentiation wrong? Like, did I just get the wrong answer? Is the second thing I wanted to point out here. What do you guys think? Did I make a mistake maybe? Or is this whole implicit differentiation shenanigans? Maybe there are some situations in which implicit differentiation doesn't work. You think maybe that's the case?
I have a question.
Yeah.
So when you did that, I don't know if this is part of the problem, but you did 1 times y. So it's supposed to be the 1 is the
derivative of x.
Of x, yeah. So wouldn't it be 1 where it says y prime as well, or no?
Well, yes, if I was writing it out, being very, very pedantic, then yes. Derivative of x would be 1 times y plus the derivative of y is 1, but I just differentiated a y term. So the chain rule takes effect. I have to multiply by the derivative of the inside. Right? I'm thinking of like the y as an f of x, right? To like a 1 power. Right? And so the power rule says I can bring that 1 down, comes the 0 power because I subtracted 1, then I multiply by the derivative of the inside. So the derivative of that is really 1 times f prime, right? Which is just f prime, which is just y prime, right? So technically, yes, the derivative of y is 1, but because there's an inside function, I have to multiply by the chain rule. I have to multiply by the derivative of the inside because of the chain rule. So that's what happens there. Derivative of y is y prime. So that's the first thing. But then I can solve for the y prime and I get this. And the question is that correct? Well, of course it is, because if the implicit differentiation doesn't work, what that means is that the chain rule didn't work. And if the chain rule doesn't work, then what are we doing here? Because we build so many things on the chain rule. Like if the chain rule is wrong, like all of calculus is wrong, forget about it. It's not, yes, they are the same. We know that our y is 1 over x, right? So this means that if I have y prime equals minus y over x, well, that is equal to minus 1 over x, because my y is 1 over x. And so that's actually 1 over x squared. The answers are the same. Just in a different form. One involved the y being a part of the answer and one didn't, but they're actually the same. They're equal answers, okay? So we could have done this 2 ways, and the implicit differentiation way seems more difficult here. Also seems like, well, what's the point if I could have just solved for y? At this point, you're probably wondering, so implicit differentiation is not necessary, right? I mean, really, why did I need it here, right? Like that's definitely a reasonable criticism. That if you were to tell me like why did I need to know this? So I'm not going to really harp on that yet, but allow me to show you another example. Let's look at this one. Find y prime. Okay, so let's actually talk about this without implicit differentiation. Can we solve for y? I'll tell you that yes, we can. Yes, we can. It's about hope. How would you solve for y here to be able to do things the old way and avoid implicit differentiation?
You just bring everything to the other side and solve for y?
Yeah, how? Someone got kicked out here.
Like you start by like,
yes, I
you
can
divide by that first side. Yeah, do you just start moving like the terms over, and then like, so you start with the 5x squared thing, divide that by like the other side.
Wait, so we have
They compare
5x
y,
squared
so-
plus 2xy plus x to the fourth y squared minus 4x cubed. And then what? For some reason, I just don't feel comfortable today. I just feel like I'm positioned weird.
Couldn't
I was
we?
doing it another way.
Madeline?
I was
Yeah?
doing it a different way as well, where
What?
I kept 5x squared plus 2x times y on the left, and I moved x to the fourth times y squared to the right, so it was minus x to the fourth.
So 4x cubed minus x to the fourth y squared?
Yes, and then I divided by 5x squared plus 2x.
Okay, and then what? Because there's still a y here. So how would you differentiate that without implicit differentiation? Like if you want to use x,
See,
x
I did it.
Yeah, what did you try?
I don't even think what I did was legal then.
So you can solve for this. Let me, maybe I'll write it out in a different way that might hint to you what you would do. So here's how I would write it down first. Now, do you see what to do? Let me ask this, what kind of equation is that? If I'm focused on the y, I want to solve for the y, what kind of equation in y is this? Should look familiar. You dealt with equations like this in algebra class all the time. Very common type of equation.
Is it a polynomial? The y squared?
You could look at it as a polynomial, sure. You want to get a little bit more specific? What kind of polynomial? So the y is the variable that I care about here because I want to solve for it. What if I thought of these x's as just some numbers? Like think of this as A, think of this as B, think of this as C. What kind of equation am I looking at? Right, what I have here is ay squared plus by plus c equals 0. What kind of equation is that? Starts with Q.
Quadratic.
It's a quadratic. So this is actually quadratic in y, which means I do know how to solve this. Gasp. It's quadratic. Okay, so one of the skills you were supposed to learn in algebra class and a little bit more in pre-calculus class as well, that unfortunately a lot of students don't pick up on. I don't know because it wasn't emphasized or whatever, but the idea of forms of stuff, the idea of, oh, a quadratic equation has a certain form, a linear equation has a certain form. Like it doesn't have to be exactly what I expect it to look like. Like it doesn't have to be like 5x squared plus 2x minus 7 equals 0 for me to recognize it as a quadratic. The 5 could literally be anything that doesn't have an x in it. The 2 could literally be anything that doesn't have an x in it. The 7 could literally be anything that doesn't have an x in it. As long as I have something times an x squared plus something times an x plus something with no x's equals 0, it's quadratic, right? So the idea of a general form that you can manipulate, right? You want to be able to think abstractly on these things. Because once you recognize something as that form, now something that was very difficult should be very easy, because we do know how to solve literally any quadratic. We have a standard strategy here. It's called the quadratic formula. So by the quadratic formula, I know that my y is going to be minus b plus or minus the square root of b squared minus 4ac all over 2a. So here, this becomes my y is going to be minus b, 5x squared plus 2x, plus or minus the square root of b squared plus 2x squared, minus 4, well, it becomes a plus because it's minus 4 times a times c, that's an x cubed, all over 2 times a. So that is my y. So now find y prime, right? To which I say, nah, no, I'm not going to do that. Like no, it's not even fair for you to ask me to do this. Like, why would I want to find y prime in this situation? Yeah, no. like that's going to be like a quotient rule with like some crazy chain rule in it. Like, no, just no. Like you can't get me to do this, right? So standard way is not desired. Let's talk about with implicit differentiation now. Do we have the same kind of problem? Is it going to be some crazy, complicated thing? Well, I have, let's see here, 5x squared plus 2x y plus x to the 4th y squared equals 4x cubed. Now, for implicit differentiation, I don't have to solve for y. Like, y does not need to be explicitly known. I don't need a formula for it. I can just go through and start differentiating, right? So I can go through, I can differentiate the first term by the product rule, right? So differentiate the first term, leave the second, plus leave the first term, differentiate the second, plus, again, product rule here, differentiate the first term, leave the second, plus leave the first term, differentiate the second. Over here, differentiate that term. Notice that every time I differentiated the y term, I multiplied by a y prime, because that is what implicit differentiation tells me to do. Also here, I use the product rule. Here, I use the product rule. Here, I use, well, the power rule with constant factor rule. Right, just left the 4, differentiate the x cubed, which is 3x squared, I get 12x squared. So yeah, and now the calculus is done. I've done the differentiation. At this point now, it's just algebra. And the nice thing about this is, it's always going to be kind of like a linear function. It's not going to be quadratic or anything like that, because I'm not going to get a y prime squared or anything. So it's just a matter of moving everything without a y prime to one side and leaving everything else. So at this point, I would have my y prime times, well, the 5x squared plus 2x. That takes care of this term. and then I would have plus, then I would have plus 2x to the fourth y. That takes care of this term. And that's all my y prime terms. Over here, I have 12x squared. Then what I'm going to do is I'm going to subtract the 10x plus 2y. That takes care of that term. Then I'm going to subtract the 4x cubed y squared. That takes care of that term. And my 12x squared was already that, right? So sometimes when these things get really long and I'm moving stuff, I'd like to strike it out to remind myself that I moved it so I don't miss anyone. It's actually very common, especially in like a test when you're rushing, to like miss someone that you're moving over when something is this long. So I like to like strike them out as I move them so I know, okay, I already dealt with this guy, don't have to worry about that guy anymore. But ultimately we get here, right? And now I can just solve for y prime. So it's going to be 12x squared minus 10x plus 2y minus 4x cubed y squared all over 5x squared plus 2x plus 2x to the fourth y. Now that looks very, very complicated, very huge, but I mean, conceptually speaking, it wasn't actually hard to do that. If you think doing this would be easier, be my guest, you're welcome to try that. Use the quotient rule with the chain rule and all of that, and tell me which one you like more. If you like doing it this way, perfectly fine with me. You can spend the entire exam on this one problem, and yeah, if you get it right, I will give you credit. If you want to kind of imagine, so remember like here, where I could show you that, oh, the two answers are equivalent. All I have to do is figure out what the y is and plug it into the other one, and you'll see that they simplify to the same thing. In that same way, if you want to know what the answer would look like if you were to do this directly, just imagine this guy that we have here plugged in here, here, and here. And imagine the monstrosity that you would have if you were to do this directly. So if you want to have an idea of what doing this directly would look like, imagine that. Imagine this thing in those three positions. That's what your final answer would look like. And if you think that's a fun time, and you're like, yeah, I'm all about that, that's how I want to do it, I'm not going to blame you. I don't think it's going to work out in the end, but you know, to each their own. So at this point, you might have another thought. Okay, so I could have done this without implicit differentiation, but I probably wouldn't want to. So is that how I should think of implicit differentiation? Implicit differentiation is not necessary, but may be recommended, right? There are times when I definitely don't want to actually do it the old way that I know about. And implicit differentiation kind of makes things easier on me. So maybe that's it. It's an optional technique. We can try it. We can try it when we don't want to have to deal with things directly. We don't want to have to waste our time figuring out how do I solve for y here, and then at the end of the day still having to do the calculus and then having to simplify. It's going to be too much. So maybe that's the case. Allow me to show you another example. Find y prime. Now, admittedly, this one doesn't actually look as bad as the second one, but there is going to be a hiccup. Okay, so go without implicit differentiation. Solve for y. so that we can differentiate. So that we can differentiate as usual. Okay. So how do we solve for y here? Give me some ideas. It's also a polynomial. Pretty innocent looking, pretty simple. What would you do? You have to solve this for y. What would you try?
I have a question.
Yeah.
I just tried solving it, and like when you get the y's to both sides, they end up like canceling each other out in the end.
How? What did you do?
So I did x squared plus y to the 7th minus 3 equals 2y. Then I did x squared minus 3 divide over 2 equals y minus y to the 7th.
So x squared minus 3 over 2 minus y to the 7 over 2 equals y?
No, equals y minus y over 7. Oh, I did it wrong. Never mind.
Yeah. Yeah, I don't think you could do that. Okay, so I mean, I'm going to save you a little bit of time here. So solve for y. Impossible. Okay, so now here's some facts, some cold hard truth, that not everything has a solution in some sense. So it's actually impossible to solve for y here. And I want you to appreciate, I don't mean it's very hard. I don't mean you would need a supercomputer to do it, or you need to be a very brilliant person to do it. I mean, it is literally impossible. Like the smartest math person in the world could not do this. The smartest supercomputer that will ever be built at any point in the future could not write down a nice function for y here. It's impossible. We know this because there was this very young mathematician by the name of Galwa. He was French. So that's how his name is written. You know, the French, they don't care about how letters sound. They just like, I feel like I want to put an OIS here and pronounce that as wa. But that was his name, Galwa, Everest Galwa. Very passionate young man, political activist, you know, one of those hearts of fire kind of guys, wears his emotions on his sleeve, very forceful, really into his beliefs, and he wasn't afraid to, like, you know, stand up for them. Very passionate young man. He also was a mathematician and had a bright future ahead of him, but he was, you know, a little bit of a hothead. And so this was, you know, 300 years ago or something like that in France. Yeah, this guy went for what he wanted, stood up for what he believed in, fell in love when he was young, early 20s, things of that sort. However, the girl he fell in love with already had a guy. And in those days, of course, it's all about chivalry. You try to mess with my girl, I'm going to challenge you to a duel. So he's like, bring it then, right? Of course, later that night, he realized, what the hell am I doing? I'm going to lose. This guy is going to kill me. I'm probably going to die tomorrow, right? So that night, he spent that night writing down all his thoughts on the mathematics that he's been studying on his own. He wrote volumes that night, like a man possessed, wrote down everything that he's been studying over the years, what he's discovered, the things that he wanted to study further when he went to university, all that stuff. Just write down all his mathematical thoughts. We have copies of his notes where he's literally writing in the margin, I have not time, just trust me, this is true. I proved it before, but I don't have time. This is true, let's move on to the next thing, blah, 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 and he's writing down all his thoughts. Among those papers we use today to develop something called Galwa Theory, which is something that you don't see until you're a graduate student in mathematics. So it's really heady stuff. Like most of you haven't seen any of his work yet. Very young man, but he was thinking ahead. Among those things that he wrote down, among his theory, he was able to prove that once you have a polynomial of degree 5 or higher, there is no general formula. You know, like how we have for quadratics, there's a quadratic formula. I can literally use that formula on any quadratic. It turns out that once you get to degree 5 or higher, no such formula exists. There is no general formula to write down the solution to a 7th degree polynomial. You can't write it in terms of any mathematical symbols that you would understand. You wouldn't be able to write it down in radicals or divisions or multiplications or anything of that sort. And he kind of proved that. You might get lucky. You might have a nice 7th degree polynomial where it has a nice solution, but there's no general rule. You can't solve these in general. Sometimes it's literally impossible to write down the answer. So we actually know this for degree 5 and higher. And this particular 7th degree polynomial that I just gave you guys is such a polynomial. It has no solution, no answer. We know this because of Galois. We know we cannot solve this, and it's not because we're not smart enough or we're not working hard enough. It doesn't have an answer in anything that we would be able to articulate. So there's that. So it's literally impossible to actually solve for y here. So yeah, that kind of blows our original strategy out of the water, doesn't it? So yeah. Implicit differentiation is the only game in town here, if you care about finding derivatives. It's not nice, it's not annoying, it's not recommended, it's not if I feel like, it's like, dude, if you want y prime, this is the way to go. There is no other way, right? You can't like just not know implicit differentiation. You're not going to get very far. Functions like these actually show up all the time. In fact, this curve is a very important curve. It has a name. This curve, the x squared plus y to the 7th minus 2y equals 3, is called the folium of Descartes. Descartes, another giant. I think therefore I am guy, that philosopher that most people think is a philosopher. He was also an amateur mathematician, did a lot of mathematics on his own. He's actually the guy who invented the XY plane, believe it or not. Like that XY plane that you guys drew, it didn't exist forever. It only started existing like 300 years ago, and it revolutionized mathematics. You mean I can draw a picture of an equation? Is that what you're telling me? Like, yeah, we didn't know we could do that until Descartes. Has an S here. Folium of Descartes. So that guy, Mr. I think therefore I am, was studying this curve. It was a very important curve. It's actually not a function. It doesn't pass the vertical line test. Looks something like this. Symmetric. So not a function. Does not pass vertical line test. It's just it's a curve, right? But it has a lot of important applications. And so, yeah, I might want to study this curve in terms of calculus. I might want to be able to find a tangent line to this curve for whatever reason. And I'll tell you some reasons later on. But here's an example of something where I want to be able to do calculus, but I literally can't do it the way that we were doing it prior to 2 classes ago, or prior to last class. Yeah, implicit differentiation, only game in town. Let's actually see what we would get. So x squared plus y to the 7 minus 2y equals 3 This means that 2x plus 7y to the 6y prime, remember whenever I differentiate a y term, I have to multiply by y prime, minus 2 times 1 times y prime equals 0. So now here's my y prime. So now I have y prime times 7y to the 6 minus 2 equals minus 2x. And so my y prime is equal to minus 2x over 7y to the 6 minus 2. So yeah, impossible for me to write down the function, but finding the derivative of the function wasn't actually that hard. Yeah. So, I mean, as you'd really know, and I kind of harped on this a little bit last time, the hard part of calculus isn't the calculus. The calculus part is always easy. The algebra part is hard, sometimes nigh impossible or impossible, right? So yeah, I could solve for the derivative here pretty easily. Now you might be wondering, well, it has a y in it. And I just went at length tell you someone's life story about how we can't solve for it. So we can't solve for, how is this answer even useful? So sure, I can find a derivative, but if the derivative has the original function in it and I can't solve for the original function, is the derivative even useful in this case? Like if I don't know what the y is, I'm not going to know what y to the 6th is, and I'm not going to be able to actually calculate the y prime, am I? Well, not so fast. Here's another example that we'll do as a follow-up example. Given x squared plus y to the 7th minus 2y equals 3, find the equation of the tangent line to the curve at, what point did I look at here? 2, 1. So I claim that we can find a tangent line at 2, 1. First, is 2, 1 on the curve? Well, let's check. Set x equals 2, y equals 1. This means that x squared plus y to the 7th minus 2y would be equal to 2 squared plus 1 to the 7th minus 2 times 1. This is equal to 4 plus 1 minus 2. That's 5 minus 2, that's 3, which on the other side of the equation is 3. So yes, this point is on the curve. Now, I'm going to say something that might be surprising to some of you, but this part is actually not that difficult, although we might need a computer to help us. Even if we can't find a direct formula for some function or expression, it turns out that we can find coordinates on that function relatively easy. Fact, finding coordinates on a function or curve is, in general, much easier than solving for an explicit formula. Numerical analysis, that's the area of math that deals with a lot of this stuff. and other approximation techniques. Right. Now, numerical analysis, chances are none of you have to do that class, but I just want you to know that we have standard procedures to, if you give me a curve, that I can use to find coordinates on that curve. And yes, sometimes it comes as an algorithm where you have to re-crunch numbers and keep getting closer and closer to the answer. And so it's going to be convenient to use like a computer to help you, but it's doable. Like you would be able to tell a computer, find me points on this curve, and it will be able to figure out that 2, 1 is on the curve without even knowing what an explicit formula for the curve is. So while it might seem strange, I cannot find a formula for this curve explicitly in terms of y, but I can find particular coordinates on this curve, like a coordinate of 2, 1, I can tell you is on this curve, right? And I can do this for a bunch of points. So you can ask me, when x is 17, what is y? And I'd be able to tell you, right? Which is weird. I don't know the formula, but I'd be able to tell you what the y value would be when the x value is a certain thing. It's kind of weird, but yeah, that we do have mathematics that can handle that. We don't have mathematics that can solve for a nice, what we call analytic formula. So to be able to find the coordinates is a very doable thing. Okay, so now let's actually do the problem. So we know the slope is going to be y prime evaluated at 2, 1. Well, that means it's going to be minus 2 times x, right? So it was minus 2x, and x is 2, over 7 times y, which is 1, minus 2, right? I'm just using this derivative formula that we had up here. So this is equal to minus 2x over 7y to the 6 minus 2, evaluated at 2, 1. So I can find the slope, and that's going to be minus 4 over 5, right? That's going to be my m. Then we have the point x1, y1. Well, that's going to be 2, 1. So this means tangent line is y minus y1 equals m x minus x1. So that's going to be y minus 1 equals minus 4 over 5 x minus 2. Or I can say that's y equals minus 4 over 5x. This will be plus 8 over 5 plus 1, which is 5 over 5. And so this means that my y is minus 4 over 5 x plus 13 over 5. And so on this curve, which is impossible for me to find out a formula for it, at 2, 1, I can find a tangent line. And the equation of this line, so this is at 2, 1, and the equation of this line is y equals minus 4 over 5 x plus 13 over 5. Now, here's the nice thing about tangent lines. Remember, and we'll do more on this later, when we get to a topic called linear approximation. Tangent lines approximate a function at a point. It is literally a linear approximation. The more we zoom in, the better. So, in other words, here is the folium of Descartes. And here is the tangent line they are very similar here. So similar, we may use the equation of the tangent line instead of the function itself. So this is another power that calculus gives us. We can have functions that are very important to us that we really want to be able to study, but they're hard to handle because we don't have a formula for them. However, if we're able to find a tangent line to points where we care about on that function, then we could literally use the equation of the tangent line instead of the equation of the function itself. So if I wanted to talk about, well, what is the rate of change of this function? Well, it's -4/5. How will it behave if I'm at x equals 2, but I move a little bit over to the right? It's going to decrease. What if I move a little bit over to the left? It's going to increase. Like I can know all these things about this function that I don't even know a formula for it, right? I can actually use calculus to talk about the behavior of a function that is impossible for me to get my hands on, right? And we'll do some of that a little bit more, where we'll actually use a tangent line to approximate a function. So here's a very important function, very nice graph. However, I can't solve for the y. However, I can do calculus on it anyway with the power of implicit differentiation. And because I have numerical analysis, I can find coordinates on that graph. I can find tangent lines at any points. And if I'm at a point that I care about, I can use the equation of the tangent line in lieu of the equation of the function to talk about the behavior of the function. And so calculus helps us to do that as well, which is it's pretty neat. So while I don't know this function, I can actually study it in a lot of depth. The caveat is I just have to study point by point. I can't just study it as a general concept. However, if you were to tell me, I'm interested in when my x value is 15, we can zoom into 15, we can set up calculus at 15, and I can tell you how the function is going to behave at 15, but how it's behaving in general, it's harder to say. But I can do this locally, and the power of calculus, with the help of implicit differentiation, allows us to do that here. So that's just something that's really cool with this example. So yeah, implicit differentiation is necessary sometimes. So we need to know it. So that was just an illustration of how implicit differentiation kind of fits into our overall thing. Sometimes it's optional. Sometimes you'd want to do it as opposed to doing things normally. Sometimes it's the only game in town. You have to know it. And knowing it, even in cases where it's impossible to solve for our functions, can still be useful because I know how to address functions point by point. More examples. Find a, okay, it's not, move over a little bit. Find y prime equals dy dx if, where is my other example? E to the x plus y squared plus ln of x plus y equals 3. Okay. All right, walk me through this. How do I differentiate e to the x plus y squared? How do I differentiate e to the anything? Well, the derivative of e to the u is what?
e to the u.
No. Notice that I have a ddx here. X is the independent variable, which means u is some other function.
Isn't it u prime e to the u?
It's u prime e to the u, right? We differentiate an exponential by taking the derivative of the power times the original function. Okay, what about ln? The derivative of ln of u is
U prime over U.
u prime over u, right? Remember, you need to know the formulas. They are your templates. They tell you what you have to do. So when I ask you, how do we differentiate this? That's what you should think of. What rule applies to the thing I'm looking at? So I'm going to find the derivative of the power and multiply by the original function. Now, what is the derivative of the power?
One plus 2y.
No.
Wait, no, I'm sorry. No.
Okay, so you want to try again? I'm finding dy dx. Y is therefore some function that I might not know a formula for. So it's an inside function. So how do we deal with that? So what is the derivative of the power? Someone else want to take a crack at it? Derivative of x plus y squared. Remember your training, grasshoppers. We're differentiating implicitly. How do we do that?
Wouldn't it be 1 plus 2y to the y prime? Not to the y prime, times y prime.
Times y prime, right. That's implicit differentiation. Whenever I differentiate a y term, multiply by y prime. You cannot forget that because you'd have the wrong answer. Okay, so moving on. Derivative of ln of x plus y. I know I want u prime over u. So the thing inside the ln goes on the bottom. What is the derivative of that thing?
Wouldn't it be 1 plus 1 to the y prime? Not to the y prime, times y prime.
Yeah, okay.
Sorry.
Thank you. Derivative of 3 is 0. I do like that you correct your language there. I mentioned this briefly before, but language is actually important. So when you say to the y prime and you're like, oh, no, I mean multiply by y prime, it's actually very important. You know, one of the reasons why is that your language is directly connected to your cognitive abilities because you think in your language. I've seen people like that I've been tutoring where, you know, like their mother tongue would be Spanish or something else. And I would always notice that if they're like doing arithmetic or something, they would mumble in Spanish. Like that's how they think, right? So they're talking to me in English, but then when they're working on something, they mumble to themselves in Spanish. You literally think in your language. What that means is when your language is off and it's not matching up to the actual work that you're doing, it causes like this little shift here where when you least expect it, mistakes are going to happen. So there are times when someone would do something on a test and they're like, honestly, professor, I don't know why I wrote that. I know better than this, right? So sometimes you'll be on a test and someone would actually write to the y prime because their language tells them to the y prime. And then because they're rushing, they're not even really thinking about it. They just kind of write it in a power because they have the language to say it's a power, right? So you'd have things like that where it's like, you know, you just when you're going on, it's spelled to the y prime. And you know on a conscious level that it should be multiplied by y prime, but subconsciously the language is to the y prime, and then you mess up because of that when you're rushing and you're not really thinking and you're kind of freaking out. You have to realize that when you're anxious, it's not really your conscious, deliberate brain that takes effect, right? There's a slow twitch thinking and fast twitch thinking, right? There's a deliberate thinking, and then there's oh my God, there's a tiger right there about to chase me. I need to run and not even think about it, right? There's a part of your brain that just reacts, right? And so by training your language, it helps you to train that part of your brain because language is deeply ingrained into your brain. So I actually like that you corrected yourself there. Just work on not saying it the wrong way in the first place, and that will be better. But yeah, that's the derivatives. Now we need to solve for y prime, which now this is an algebra problem. We know that we need to kind of separate things that have y primes and don't have y primes. So what I would probably do is multiply this out. So this gives me e to the x plus y squared plus 2y prime e to the x plus y squared. Here I would split the fractions, 1 over x plus y prime over x plus y. And here are my two y primes. So I'm going to leave those on one side. And bring everyone else on the other side. So minus e to the x plus y prime minus 1 over x plus y. So this guy here accounts for that. 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 Yeah, everyone's accounted for. Moving on, y prime is going to be minus e to the xy squared plus 1 over x plus y over 2y e to the x plus y squared plus 1 over x plus y. Of course, I can simplify that a little bit by multiplying and dividing by the LCDs. This is x plus y e to the x plus y squared plus 1 over 2y x plus y e to the x plus y squared plus 1. That is my derivative. Another example. Find dv dt, switching up the letters now because I don't want you to only be able to think in terms of x's and y's. If p plus 5 over v squared times v minus 0.03 equals 9.7. Now, at first, that might seem like a totally random thing to write down. Like, why did I put 0.03 and 9.7? Couldn't I just put whole numbers? It turns out that this is actually a thing. Like, I didn't make this equation up. Does anyone recognize this? No, doesn't strike a chord with anybody? Have you all taken chemistry? Or no? Are you currently taking chemistry? So this is actually an equation from chemistry. Like I didn't make this up. This is called van der Waals equation. For a specific gas. Right. So I picked a particular example because I do want you guys to appreciate that the situation that I was up here, that I was in up here with the folium of Descartes, where I'm like, a lot of people might think, okay, all right, I can see that I needed implicit differentiation here, but really it's just some math guy studying some random curve that he likes, and now I need to learn about it. Well, no. You see, implicit relationships show up everywhere, even in sciences that are not directly mathematics, like, for example, chemistry. Van der Waals, studying specific gases, came up with this relationship. Notice that it's not isolating the P or the V. It's the P's and the V's are mixed up. He just noticed that when he combines things in this way, 9.7 is the answer, like for whatever reason, right? And a lot of relationships come to us this way. It's not like we're going to invent an implicitly defined function just for the heck of it. Sometimes when you're studying things, that's how you realize things. I realize that when I do this, you know, if I decrease the volume by 0.03 and then multiply by this thing, I get this number that I can say. Like you kind of just, through just sheer like experimentation and empirical research, you can kind of come up with equations sometimes. And so this is such an equation. However, when I come up with such a relationship, I still might be interested in the calculus of that relationship. How does volume change in relation to pressure? If I increase my pressure by 1 atmosphere per minute, how does the volume react per minute in meters cubed per minute, right? Is the rate of change going to be large? Is it going to explode? Or is it going to grow slowly and temperately and I don't have to worry about it? Like, you don't know, right? You want to study these things. You want to still be able to study calculus. So it turns out we can actually do that here. So yeah, Van der Waals equation for a specific gas, we are going to figure out how fast the volume of a specific gas changes in relation to the pressure. Right, so P here equals pressure. And that's the force per unit area. And V here equals volume. That's just how much space it takes up. So yeah, I am going to go through and I'm going to find dV dP. So tell me how to find dV dP. Which, I mean, I can rewrite this a little bit. Move this down. We have, I guess, P plus 5V to the minus 2, because I don't want you to think you have to use the quotient rule, even though I kind of explained to you when and when not to use the quotient rule. Hopefully you won't waste your time using the quotient rule here. Okay, what's the derivative of that?
Wouldn't it be 1 minus 7v to the negative 3 power and parentheses?
Minus 7? Why minus 7?
It'd be minus 10.
Minus 10. I'm sorry.
Minus
I don't
10
know why I did
V
that,
to the
negative 3 and parentheses. Then beginning of parentheses would be 1 minus 0. And then it would equal 0.
No, that's wrong for a couple reasons. What is wrong?
You can't differentiate with the two variables like that. Right.
Okay, so what are we missing? There's an overarching thing that was missed here. What is that?
It's v to the prime. We were supposed
You missed
to
the V prime because V is the yeah, and so this should be V prime here too, but it's still wrong. Why? Yeah, V is your dependent variable. So yes, whenever you differentiate a V, you definitely need that V prime, but it's still wrong. Why is it still wrong? originally we had p plus 5v to the minus 2 times v minus 0.3. How do you differentiate something like that, like overall? What framework should we be differentiating in? What do you think?
Would it be, I'm sorry, would it be p plus 5v to the negative 2 would be f, and then v minus 0.03 would be g?
Okay,
So
and what does that mean? What does that mean? How would we have to differentiate that then?
It would be f prime times g.
Right, yeah, what is that? What is that called?
It's the product rule.
Product rule. You need the product rule. So remember your training, grasshoppers. As I mentioned, all our derivative rules have to be obeyed. Product rule is still a thing, quotient rule is still a thing, chain rule is still a thing. The only difference in implicit differentiation is when you differentiate the dependent variable, you multiply it by a prime, right? But product rule is still a thing, which means I need to differentiate one, leave the other, then differentiate the second, leave the first. So the derivative of the first one is 1 plus 1 minus 10v to the minus 3v prime, leave this one alone, plus leave the first one alone, and multiply by derivative of that, which is v prime, equals 0. So that's what that would look like. I needed the product rule. So now I need to solve for the v prime. That's the guy that I care about. So I would multiply out 1 times v, 1 times 0.03, minus 10v to the minus 2v prime, plus 0.3 v to the minus 3v prime, plus pv prime, plus 5v to the minus 2v prime equals 0. And here are my v prime terms here. So I have v prime times 0.3, times p plus 0.3 v to the minus 3 minus 10v to the minus 2 plus 5v to the minus 2 equals 0.03 minus v. This guy I can combine into minus 5v to the minus 2. And so my v prime equals dv dp is going to be equal to 0.03 minus v all over p plus 0.3v to the minus 3 minus 5v to the minus 2. Okay. So remember your training. The derivative rules are still in effect, right? The implicit differentiation, the only difference between what you were doing now and what you've done before is that whenever you're differentiating an independent variable, you multiply by the prime. Think about this for next class. What is the derivative of x to the x? We'll use this to segue into the next topic. As for what your test grades are, I need a little more time. I think by tomorrow I'll have those out to you. I'll send out an email as well as instructions on how to look through the test, because along with your test, there'll be a rubric. So you'll see how I graded it. You'll see what you got points for, what you lost points for. So I would send you information on how to do that and how to respond if you find a grading mistake or anything like that. And we can move on from there. Yeah, but for now, we will stop there. Yeah. So, but think about that. How would you differentiate x to the x? So we'll deal with that next time, and it will lead us into another technique that we want to explore. As well as next time, we'll probably also start doing Lopesell's rule, I think, which would be pretty cool. And you'll finally get those memes that I put in a quiz a while ago. So it'd be nice to see that in hindsight. That being said, thank you for your time and attention. Have a good rest of your day. Have a good weekend until I see you guys in the next one. Ciao.